Hi, everyone. My name is Aditya, and I am a final year medical biosciences student studying here at Imperial College London. So, welcome to this crash course on IB chemistry. I've been teaching chemistry for the past 2 years now. So welcome. And so, we're going to start with the first four topics, beginning with Unit 1, and that is stoichiometric relationships. So this consists of three subunits. 1.1, which is introduction to the particulate nature of matter and chemical change, which we're covering in this video. And then after that, we're going to look at the mole concept and reacting masses and volumes. So without further ado, let's begin. So the fundamental basics of chemistry is the states of matter. So I'm sure you are familiar with this from your prior knowledge or from IGCSE or MYP chemistry. But so there are three states of matter, which is solid, liquid, and gas. And we can interconvert between the two in many cases. So if we take the example of water, or H2O, for example, H2O as a solid would be ice. And to convert that into a liquid, to convert a solid into a liquid, we undergo melting to get water as a liquid. And then from a liquid to a gas, we do evaporation to get, if we're going with this example, water as a gas, which is steam. Then we can go actually back from gas to liquid via condensation and back from liquid to solid via freezing. So condensation, you might notice on the side of a cold can of Coke, for example, you would notice like water droplets forming, and that is condensation. And from a liquid to a solid, that's just like making ice, freezing. From solid back into to gas, we can make a direct conversion without bypassing the liquid phase, and that's called sublimation. And going from a gas directly into a solid, bypassing the liquid stage, is deposition. So these are all what in this example where I'm talking about water, we're talking about physical changes. So in physical changes, there's no new substances being produced. So in this example, we are changing the state of matter of water, but we are not making any chemical change to it. It's just H2O at the end of the day, but as a liquid or a solid or a gas, but it's still just H2O. Nothing new is being formed. Whereas in a chemical change, there is a formation of new substances. So in the reactants, the bonds within the molecules are broken down and new bonds will form to form new products. So atoms are rearranged in that process, and that is physical and chemical change. Now to talk about elements, compounds, and mixtures. So elements, this is like everything you see on the periodic table. Elements cannot be broken down into a simpler substance by chemical means. So this is an IB definition, but also I would add that, and they have a specific atomic number, which is the number of protons. So the number of protons is sort of like the ID card of an element. Like any atom of that element would have the same atomic number or proton number. Some elements exist as diatomic molecules. So an example of this is the halogens. So group 17 elements, or also known as group 7 elements. So this includes like F2, like fluorine, Cl2 chlorine, I2 iodine, so on and so forth. They all exist as diatomic molecules. So basically it means that they are two atoms that are bonded together. So that's what this like little tube signifies. On the other hand, a compound is formed from two or more different elements chemically joined in a fixed ratio. So there's endless numbers of compounds. For example, C6H12O6, that's glucose. There is CH3 CH2OH, that is ethanol. There's also, I don't know, H2O, water, going on, so on and so forth. And finally, we have mixtures, which are homogeneous or heterogeneous. So a mixture basically is when you have different substances, so elements or compounds or whatever, and they are mixed together, but they are not chemically combined. So they're not bonded together, basically. So each of the substances in that mixture retain their individual chemical properties because there's no new products being produced, no bonds are being broken, nothing is being rearranged, everything is staying the same, but they're just mixed. So we have two different types of mixtures, homogeneous and heterogeneous. So in a homogeneous mixture, we have constant composition throughout the solution, throughout the mixture. So, for example, if I have this container with my mixture, and if I have compound A and compound B represented by like this orange and blue kind of dots, if it was a homogeneous mixture, it might look something like that. Basically, it means that the components of the mixture are evenly distributed throughout the mixture. There's a constant composition throughout the mixture. So essentially, if I took like this part of the mixture and that part of the mixture, you would notice that they're essentially the same. They both contain 2 blues and 2 oranges, same on the other part of the mixture. So there's a constant composition. Whereas, so that is homogeneous. Whereas, if we look at heterogeneous, a good example is water and oil. So if that's our water, and if we have oil here, we notice that they have separated into visibly different phases. So we have our oil phase and our water phase. So basically, heterogeneous mixtures are not they're not mixed, so that they don't. I mean, they are. You could try to mix them, but they wouldn't allow it. Like even if you mix water and oil, you might get like little droplets of oil in the water phase for a while, but then eventually, if you left it on its own, they would separate out into different phases. So they cannot have constant composition throughout. So they have different phases, and they are very distinct. And that is because basically these substances, in this example, for example, water and oil, they cannot form intermolecular forces between each other, whereas for heterogeneous mixtures, they very often can, or they actually can, because that's how they are mixed together. Okay, next, looking at chemical equations, balancing chemical equations. So there's the law of conservation of mass, which states that mass is conserved in chemical reactions. So the total mass of products must be equal to the total mass of reactants. And so therefore, when we're writing chemical equations, it's important to balance it to represent that and to account for that. And to balance a chemical equation, we need to change the coefficients. Coefficients are basically like any number that comes in front of a molecule or element. So anything that goes in front here. So your coefficients would go in that spot. So the numbers basically. So in this example, in this example, we have this chemical equation. Feel free to pause and try this on your own, but I'm going to attempt this as we go. So we can see that there's 8 carbons on this side of the equation, and 18 hydrogens and 2 oxygens. Whereas on this side, we have 1 carbon, 2 oxygens, and 2 hydrogens. So we need to balance that. So first I'm going to balance the carbons. So there's only 1 carbon-containing compound on the other side. So it makes sense that I would add 8. I have to, so in order for that to be balanced. And there's 18, so I have to add a 9 here to the only hydrogen-containing compound on the other side. So that makes 9 times 2, 18. Now, we have 8 oxygens and 9 oxygens, plus 9 oxygens. So that's 17 on this side. And we need 17 on the other side as well. So it's O2. So I'm going to do 17 over 2. So 17 over 2 times 2 would give us 17. But we cannot, or we usually do not have decimal numbers on as the coefficient when we're balancing equations. So what we can do is instead, we are going to multiply everything in this equation by 2. So this will cancel out, and this will become 18. This will become 16. So that will become 17. This will become just 2. So when we add all that, 2 plus 17 plus 16 plus 18, we will get 53. So hope you got that right. Next, atom economy. So atom economy is basically this equation. It's the MR, which is the molar mass. For example, it's the molar mass of the desired product divided by the molar mass of the all of the reactants in a chemical reaction, and multiply that by 100 to get like a percentage, basically. So you can also use mass instead of molar mass, but you just have to make sure that the units for the numerator and denominator are the same. And basically what this tells us, the atom economy, is that it indicates the percentage by mass of all the reactants that end up in the desired product. So higher the atom economy, less waste is produced, and the reaction is more efficient. Right, so this actually brings us to the end of topic 1.1. In the next video, we are going to be looking at topic 1.2, which is the mole concept. So I hope you found this useful, and I hope to see you in the next video.